If you don't know who I am, my name is Emmanuel Schanzer. I'm a former computer scientist. I went to go work for Microsoft. My specialty was in programming languages. I always knew since I was in kindergarten that I wanted to be a teacher. Thank you, Mrs. Bidwell. And so my original plan was to go sort of make my millions in the software sector, then go pursue my passion for teaching. It turns out that working for Microsoft in the early aughts was a miserable experience. So I just skipped over the making money part and went into teaching. And I was a public school teacher in Boston Public Schools. I taught ninth grade algebra and then served as a middle school math coach for several years. And I started to do a lot of thinking about the possible connection between computer science and math. This led me to do some research. I got my doctorate in algebra education over at Harvard after a couple of years. And the dissertation ultimately became a curriculum known as Bootstrap. And I'm really lucky right now to serve as a chief curriculum architect at Bootstrap. We're the nation's largest provider of integrated computing. And that's what I'm here to talk about today. So let's do a quick look back about how we got here. Because 15 years ago, everybody was saying like, oh, everyone should learn to code. It'll be so great. And everyone sort of agreed with that. And millions of dollars got put in. NSF supported CS for All, Silicon Valley supported Code.org, and all these other organizations. And everybody was asking a set of questions. They were like, how are we going to recruit these teachers? How are we going to train those teachers? And then once we've trained them, how will we retain them and stop them from going into the private sector and making 10 times as much money? And even if we solve all of those problems, we still have to solve the problem of time and space. There's only so many hours in the school day and only so many rooms in the school building. So, and let's see, whoops. Can you guys still hear me? I just got a warning message in my browser. You guys hear me okay? Thank God, okay. So fast forward, and the proof is in the pudding, right? Like this idea of standalone CS classes has not worked out so well. So 15 years later, after tens of millions of dollars, and by the way, support of both political parties. So computer science education might be the last thing that they agree on. So unprecedented support. 15 years later, we've basically got 6% of kids enrolled in foundational CS. And only 31% of those students are female. So I would say that if you're pouring that much money and that much political capital into something, and 15 years later, you're barely over 6%, probably you need a different strategy. So at that same time, 15 years ago, we made this bet on integration. We thought siloed CS classes are not the only way to do this. They might not even be the best way. And our challenge was, how can we integrate computing and math authentically? And this is where the dissertation research comes in. Because it turns out, and this is going to be the focus of the talk, that integrating computing into mainstream subjects is not as easy as it sounds. It can be done, but the current fervor over like, let's just shove Scratch into every class possible is not going to be successful. So we wanted to do authentic integration. And we also wanted to make sure that it's a way that works for all children, right? So math teachers, for example, they have to serve every child in the school, not just the kids who opt into a certain elective. And so if we're going to do this, it has to work for everyone. So 15 years later, now Bootstrap is the largest provider of integrated in-school CS nationwide. We're very lucky to have been cited by the NSF as one of 3 curriculum providers to consider when applying for funding. 43% of our students are girls and young women. More than 46% identify as Black and Brown students. And what we're excited about is that despite being big, almost all of our teachers are not CS teachers. They don't have computing backgrounds. So, how did we get there? Well, integration has suddenly become very, very trendy, right? So, ever since Jeanette Wing said computational thinking, everyone has been chanting the phrase computational thinking. It's so amazing. It's needed in every subject. But of course, if every subject uses computational thinking already, maybe we don't need to teach computation. So I've never been able to jump on that particular bandwagon. And today's keynote panel talked about integration at length. There was so much attention paid to integrating computer science and computational thinking into mainstream subjects. And indeed, there's a million computational thinking integrated curricula out there. So I'm going to do a little quiz for all of you, not a quiz, an informal poll, which is, how many of you are feeling like there's got to be something there? There must be a way to integrate computer science into other subjects, mainstream subjects. So just chime in the chat. Do you think this is doable? Are you feeling enthusiastic about this? Rebecca says, yep, that's a thing that we could do. Eric's on board. Jennifer, I'm so with you. Yes, we do a lot of work with Oklahoma, which is an incredibly rural state. And yeah, it's not just possible, it's necessary, right? Not every school has the resources and the privilege to have extra teachers or extra rooms. Yeah. Aha, yes, Rebecca's bringing up a legitimate concern. There's a focus on test scores. So if we're not going to teach the stuff that's being tested, why would we teach it? Yeah, fully agree. And I think that's a great point to move on to the next slide too, because here's the thing. Integrating computer science into a subject like social studies does not mean and cannot mean that you tell a social studies teacher to stop what they're doing for 2 weeks and just teach Python. Like, that's not integration. That's wasting a social studies teacher's time. Not because Python isn't cool, it is, but because, as Rebecca points out, at the end of the day, that teacher has to have their kids take a test. And that test doesn't have Python on it, it has social studies. So every hour that we are stealing from a mainstream subject teacher to teach computer science, that's an hour that we owe them. And we need to pay that back. And we need to pay that back by demonstrating that the computer science we've forced them to teach or asked them very nicely to teach actually teaches the content. And there's a problem because most of the integrated curricula out there don't look anything like that. In fact, the history of CS integration, which, by the way, even though it's become trendy now, it's not like this is a new idea. This goes back to the 1970s. In fact, ever since Seymour Papert claimed that learning Logo would teach algebra, people have thought that integration is a good idea. And it turns out that the research is bad. So most CS tools have a high startup cost, right? So if you want to get kids to install Python on their computers, for a math teacher, they don't have the time to do that. And you might say, oh, well, they could just use Replit, right? Well, okay. All of us on this call probably have had to deal with talking to IT, getting a website whitelisted, right? There's a non-zero startup cost for most CS tools. And even if there isn't, there's also the cost to learning goals, because every hour that that teacher spends teaching these tools is an hour that they're not teaching the learning goals that they need to address in the classroom. So that's problem number one. And related to that is the fact that mainstream subject teachers don't just have weeks lying around. So, if it takes 3 days to get their kids oriented in code.org, that's 3 days less teaching math. So we need to cut something to make room. And I think, again, to Rebecca's point, if you talk to a science teacher, a history teacher, a math teacher, they don't have stuff that they can cut, especially if there's going to be a high stakes test at the end of the year. It's just unethical to tell a teacher to take time away from their job to do something that we happen to think is cool. And then even if they're willing to do it, or even if you could do it, these teachers didn't sign up to teach computer science. They signed up to teach ELA. They signed up to teach history. So telling them to teach something else, it's simply, they may just opt out. And of course, with teachers retiring in record numbers right now, in particular from the STEM fields that we all think are so important, forcing them to teach one more thing is extremely risky. So I'm not trying to rain on everybody's parade here. I think that there is a way forward. I mean, that's literally what we do at Bootstrap. But I think it's important to cut beyond the hype and recognize that there are some legitimate and serious challenges that we have to face if we want integration to be successful. So ultimately, the goal of integration, like the real goal, is a phenomenon in cognitive science called transfer. And transfer is like super easy to understand. The idea is if I learn a concept on the computer, for example, like doing some programming, then when I'm back on my pencil and paper math test, I can transfer my knowledge of that concept from one domain to the other. And transfer is a very well-studied phenomenon. And transfer is hard. So I'm just curious, Does anybody on this call, I know some of you, I was able to see your picture, you're a pretty young group. Are any of you old enough to remember a language called Logo? And it's okay if you don't. Anybody here remember Logo? Teresa's in it, all right. Anybody else? Eric's read about it, cool. Anybody else? David, cool. Okay, so Logo was, I would argue, one of the earliest transfer-oriented programming languages, right? It was explicitly designed to have a low startup cost, right? That's the first bullet on the slide. It was targeted in learning contexts. That's something else, by the way. Programming languages like Java, whether you love them or hate them, you got to admit they weren't intentionally designed for schools. Logo was. And in fact, Logo was even further. It was explicitly designed with this idea that kids would learn concepts like, and Seymour Papert called this out in his first paper, functions in algebra, right? So specifically oriented at transfer. Has anybody read, those of you who know about it, I see Rebecca, David, Eric, have any of you read the research results on Logo's ability to teach math? Okay. Eric, yeah, not good results. Not good results at all. And in fact, right in New York, there's a school called the Bank Street School. And the Bank Street School, those of you who know about it, it's not a typical public school. Like, if there was ever going to be a place where the teachers were tech savvy, the teachers were bought in, they really took it seriously, the school. And unfortunately, the result of the Bank Street study is computer programming doesn't really teach math. And there's been 50 years of attempts to teach algebra through computing, for example, and the general result is kids don't learn it. They learn programming, which is great, but if you're trying to fit this into a math classroom, it's not going to cut it. So why? Why has transfer been such a failure? Well, this gets back to my specialty in programming languages. It turns out semantics matter a lot. How many of you like Scratch? Anybody here into Scratch? Maybe you think Scratch is good for teaching math? I'm guessing based on the delay that either some of you are feeling less confident about that after my previous slide, or my microphone has stopped working again. Rebecca's on board, okay? Well, so here's the thing. If I'm a math teacher and you're telling me that I should teach programming, more than anything else, your programming language had better have numbers in it. And here's the dirty secret of computer science that a lot of folks don't want to talk about. Most of the languages you've all heard of do not have numbers. So I've got a screenshot that I took 10 minutes ago in the Scratch web editor. If you ask Scratch to add 0.1 and 0.2, it gets the answer wrong. And it's really easy to find other examples. And I'm not just poo-pooing Scratch. Any of you who've programmed in Java, here's a quiz. What's 1 divided by 2 in Java? Please write your answer in the chat. What's 1 divided by 2 in Java? And if you don't know Java, that's okay. You can guess. I'm on board with y'all guessing. Bingo, David nails it. Very good, David. You are entier. Yes, this is a sharp group. Yeah, in Java, 1 divided by 2 is 0. And some of you might know why, right? It has to do with Java's numeric type system, where you can have ints or floats or longs or doubles or whatever it is. But the point I'm trying to make here is that a math teacher is going to run away screaming. And frankly, they should. Because if my goal is to teach math, math has numbers. And if your programming language doesn't even get numbers right, this is probably not the best thing to teach in a math class. Here's another one. Let's talk about variables. Here's another Scratch example. So this is the math equivalent of saying x equals 3, and then x equals x plus 1. And I think all of you know that you could write the same code in JavaScript or Python or code.org, pretty much any of the popular programming languages we teach. If I run this code, what is the final value of x going to be? Feel free to put this in the chat as well. So x starts at 3, then I set x to be x plus 1. So Eric says 4. Anybody else? David agrees, yeah. So you're 100% right. The answer is indeed 4. Yep, Jennifer's got it. She's 4. It's 4. Why would a math teacher be angry right now? Like, why is that bad? Why is 4 incorrect in a math class? And I don't know if people are able to unmute their mics or to jump in. Feel free to jump in here. I want this to be as interactive as possible. Why is 4 a really bad thing here, if our goal is integration in math? Says, is it because the solution is not actually 4? Yeah, in fact, it's even worse than that. There is no solution. X cannot equal itself plus 1. That is mathematically wrong. And those of us who study algebra education know that functions and variables are where a lot of kids step off the train, right? Think of all the adults that you know who say things like, math made sense to me until it started having letters, right? Well, guess what? This is going to make that problem so much worse. And the reason is, in this example, Scratch is using something called a parameter, and it's calling it a variable. That is not how variables work. The same sin is committed in Python and Java and JavaScript and all the languages you've heard of. And you might say, well, wait a second, Emmanuel, variables in programming just work differently than variables in math. And my answer to you as the math teacher you're trying to convince is, screw that. Words have meanings, and variables were math words first. You can call a bicycle a muffin. That doesn't make it a muffin. And so the challenge here is that for kids who are just struggling to understand what a variable is in math, showing them this stuff in Scratch or code.org or whatever, that's not going to help them with math. That's certainly not going to help them understand what variables are. And then when we move on to functions, you don't even want to know, right? Like vertical line test, schmertical line test. The fact that the first function kids see in Java returns void is nuts. So all of this is to say that the reason that languages like Logo, the reason that prior attempts to integrate programming into math classes have generally failed is that no one was paying attention to whether those programming tools actually embodied the critical concepts in those subjects. So now I want you to zoom out and think, everyone is talking about how we should be just shoving computer science into biology, into history, into physics, and of course, into math. If no one is thinking about how the tools themselves either support or undermine the concepts in those subjects, this story is not going to have a happy ending. So we need to think deeply about whether the programming tools that we're teaching are appropriate. So here's what we did at Bootstrap. We start with this idea of saying, we're going to be humble about computing. We're not going to go in and say, rah, computing. We're going to start by talking to the teachers in the host subject. So if we want to get computing into physics, I want to talk to physics teachers and find out what are the concepts that are critical in physics and what are those, which of those concepts are actually challenging to teach and challenging for students to learn. Because if you pick a concept that's easy, they have no reason to try something new because they're already doing fine in the status quo. So we find the pain points, the topics that are hard. Then we try to find, are there analogies to those concepts in computing? Because if there aren't, there's no point. If there are, now you say, okay, we've got a game, right? Now we can start building something. And you use subject-appropriate tools. So if you want to embed computer science in math, use a programming language that actually has numbers or variables or functions. And guess what? Scratch, Python, they're not one of them. There are others. But the point is you got to be humble. Use an appropriate tool for the job. But the tool, while it's necessary, is not sufficient. You also need to build curriculum and work with the pedagogy, the best practices in that subject. Because the best practices in a history class are unique. They are different from what the best practices are in a math class. And these practices are more than content. I think we all know that a PhD in history does not automatically mean you're going to be a great history teacher in a public middle school, right? There's this extra set of skills, and that skill involves pedagogy. So you want to integrate computing into history class? Find out, what does history pedagogy look like? Find out how you can leverage the expertise of the teacher in that classroom already to deliver the computing content you want. But if we dive in all colonial and we say what we have is better than what you have and you're going to do it our way, we're not going to get any traction. And finally, the definition of success cannot be lots of kids learn to code. That's our definition of success, not the history teacher's definition, not the math teacher's definition. So I think it was Rebecca who said, teachers aren't going to dive in unless there's a change in standardized tests. Well, there is one other option. What if computing actually helps kids do better on those standardized tests? Right? If we can raise, teachers will actually sit up and take notice. And that must be the goal of any attempt to integrate computing into another discipline. Otherwise, we're just stealing time from that discipline to teach stuff that we happen to like. I had some other stuff that I was thinking I would share with you all, but I want to leave a lot of time for Q&A because I think this is an area that's really rich for discussion and people have a lot of questions. Because I started a little bit late, here's what I'm going to do. I'll just tell you sort of where you can find some free resources that might be helpful. I'm going to open the floor up to Q&A, and then if we have time at the end, I'll go on and show you a little bit more. So let's start. What are the resources? Well, hopefully it will allow me to switch my screen share. Let's see if it'll work. Nope, it won't. That's a pain. All right, well, technical difficulties aside, I'll transmit this into the chat here. So our research is funded by the National Science Foundation. So if you paid your taxes, thank you. That means you own it and it's free. So this is our website where we have curricula for integrated mathematics, grades 5 through 12. We do stuff with expressions and order of operations. We have a rigorously researched curriculum on algebra, which has shown statistically significant gains on standardized test questions for things like word problems, multiple representations of functions, and function composition. To my knowledge, we are still the only provider who's got this kind of evidence, and we've been shouting from the rooftops. It's not some secret sauce. It's just use an appropriate programming language and then build curricula and pedagogy that are appropriate to math. We've recently rolled out Bootstrap Algebra 2, which uses data science as the foundation for nonlinear functions. So instead of learning about line of best fit in 8th grade, we're doing parabola of best fit. We're doing exponential hockey stick of best fit. We're doing logarithm and periodic function of best fit. And this can be integrated into an existing mainstream Algebra 2 course using an appropriate programming language to bring data science into the classroom to support the nonlinear functions that are already in the scope and sequence and which are already in that teacher's textbook. If you're a data science teacher, you can use these materials to bring mathematical rigor to data science. Similarly, if you're a computer science teacher, you can use any of our stuff. It doesn't have to be a math class or a physics class. You can use any of our stuff to build a computer science class of your own that actually supports the math learning that kids need in order to graduate. All of this stuff is free. We've got materials for history, social studies, physics, and then math grades 5 through 12 That's the end of that resource sharing spiel. But like I said, everything is free. Lesson plans, handouts, rubrics, quizzes, projects, slides if you use them, Desmos activities, you name it. So I want to open up the floor to folks who may have some questions or ideas about integration. In particular, I know some of you are here from smaller or more rural schools. I'd love to hear from you. What questions do y'all have about integrated computing and how we can do this right? And Tom, for some reason, I'm having trouble clicking on the Q&A section here. So if there are questions, you may have to copy and paste them into the main chat. I don't know why tech is so messed up for me today. Rebecca asks, what is the best way you have found to motivate subject area teachers to try the curriculum? Great question. You need two things. The first is you need something to get them in the door. For us, it's students actually do better on the standardized test questions that are keeping you awake at night. Like, you need evidence. You need a research that shows that kids actually do better in the subject that you're trying to convince. You will never succeed if you're telling a history teacher that you have proof that kids learn for loops. They're going to be very impressed with you, but they are not going to care, nor should they. Right? You want to lure a history teacher in the door? Point out the fact that there are standardized test questions and AP test questions, for example, in US history, that deal with things like the Electoral College versus popular vote, that deal with things like all of these are supported by data. If you build a data-based activity that explores these things on the computer, and then as a result, you show that students are better able to articulate what happened after redlining, or what the tension is between popular vote and Electoral College, now that history teacher is going to take notice, and now they're willing to use it. They're at least willing to try it. If you just go in and say, kids will be engaged, I mean, some of them might jump in, but those are not the ones you want. The second thing you need, though, is when they walk through the door, because now you've got them in the door with results, you have to have professional development and curricular materials that actually look like history materials. In our case, they have to look like physics for our physics curriculum. They have to look like Algebra 2 for our Algebra 2 curriculum. If they just read like you took some random off-the-shelf class in like Python or Scratch, and you're like, here's a great lesson plan for you. If you change if you change the name of the project to voting, it counts. That's not going to work. So this is why I was really concerned about some of the things that I've been hearing over the last year, even some of at the keynote panel, which is, yes, integration, I think, is the way to go. I think it's a fantastic idea. But we can't be so enthusiastic that we let the mandates and the funding run ahead of what's even been developed. And there's a lot of stuff out right now that really does feel like traditional CS activities that have been picked up, dusted off, and repurposed as something that a math teacher would jump in on. So we need to take the math teacher and the physics teacher and we need to take these discipline teachers seriously. David says there's a fear from admin and teachers that teaching through CS will not work and are afraid to move out of there. Yep, absolutely. And that fear is justified, right? Maybe it's coming from paranoia. I think in many cases, perhaps it is. But it may also be coming from people who actually know their research. And they know that the history of computing integration has not been a good one. So they have every right to be concerned. They have every right to say, I want to see the results first. And so that's one of the reasons why we took our time to actually do some control group testing and published our results about student performance in their subject area. Jennifer says, I'm curious as both a math and a comp sci teacher, how to get more kids access to computer science. I'm at a school that I only offer one class of computer science, but I've taught algebra for 15 years. I want to give those kids more access. Yeah. Well, hey, Jennifer, obviously grain of salt, right? Because this is my dissertation. This is, what I do. But we have a curriculum called Bootstrap Algebra. It is designed to be something you can sprinkle across a traditional Algebra 1 course. We cover, at the start of the year, order of operations. I know that's not an algebra skill, but you and I know that every algebra teacher in the world wastes a lot of time having to review it. So we cover that. We cover domain and range. We cover functions in depth. We cover function composition. We cover word problems. We cover multiple representations of functions. We have material from our Algebra 2 and Data Science course for students to look at real data and think about deriving linear functions, right? So we're doing point slope formula stuff. We have a ton of material for you that uses a programming language that has been designed from the ground up to act like algebra, to support algebraic concepts instead of undermining them. Even the error messages in the programming language have been designed for student learning. And the reason we have this is that we built it ourselves. We realized that none of the programming languages out there were appropriate for math instruction. So we had to roll our own. It looks a lot like Python, but it acts like algebra. So all of this material is completely free. You can use it in the context of your Algebra 1 class. You can use it without having to sacrifice 2 weeks of instruction to get kids up to speed. The language is easy to learn. There's an accompanying student workbook that connects this directly to pencil and paper math problems. And we have evidence to suggest that not only will all of your algebra students get exposed to programming, but they will also do better on traditional Algebra 1 problems. So I hope that's helpful. Happy to talk offline. I believe you have my email address already. Just in case, I'll type it in the chat. Feel free to reach out to me directly if you like. Rebecca asks, how comfortable do teachers need to be with programming? They don't need to be comfortable at all. In fact, I don't want them to be, Rebecca, because a lot of teachers come to our PD being like, oh, I'm a computer science teacher who's taking over a math class. I've been doing C++ since I was in diapers. And they're because they're coming at this thinking that variables work like the way we saw in that earlier slide, x equals x plus 1. And they have to unlearn the non-mathematical habits that they picked up learning C. So I prefer a room full of teachers who've never programmed before, because the only mental model they have, in the case of math, for example, the only mental model they have for functions and variables are actually functions and variables, which means that the programming experience builds on their expertise and builds on their intuition. A math teacher who's trying to debug a Scratch program has to throw away what they've learned about the way function composition works, because that's not going to help them debug it. So for us, it's about lowering the barrier to entry and meeting teachers where they're at so that they can use their experience and intuition to jump right into the programming. Rebecca adds, yeah, they don't feel confident. Of course they don't feel confident. And look, I mean, I wish I could get you to come to a Bootstrap PD. When we do our PD, we're not sitting there. We don't spend even 30 seconds telling teachers how important computer science is. We don't spend 30 seconds telling them how engaging or wonderful computer science is. In fact, that's on purpose. I mean, I'll say it right now. All of this hype about getting integrated computer science, if we go to these teachers and we say computer science is great, we are going to lose the battle. They don't care about how great computer science is because that is not their job. They're there to teach social studies. They're there to teach biology. If they come to a PD and you're wasting their time telling them that computer science is the future, they're just going to shut down. You need to go in there and say, biology is important. And what do we know about biology? Well, we know that these concepts are critical. We know that these concepts are things that students struggle with, right? Raise your hand, biology teachers. How many of you have had kids struggle with Punnett squares? Well, once they're bought in, once they realize that you're speaking their language, that you're being sensitive to their subject area needs, now their minds are open. Now they're willing to listen, not to how good computer science is, but about how computer science is going to help kids understand genetics in biology. And that's where you have to go. So, major takeaways. Do not go in rah-rah computer science. That's a waste of time and you will shut them down. Number 2, make sure that you're focused on the learning goals in the host discipline. You want to get it into pre-algebra? Great. Find out what pre-algebra teachers are struggling with. Be sensitive to that. Number 3, use a programming tool that supports the learning in that subject. And I hate to say it, but a lot of the tools that are being pushed right now that are popular, they're wonderful. Look, I love Scratch. I love Java. I would never let them in a math class, ever. There's a lot of great people doing great work in the field of authentic integration, choosing subject area tools. Start with them. And then finally, provide a curriculum and a pedagogy that is built around the material that they already teach. And then show up with results, show up with data showing that this has actually worked. Jennifer asks, do we have any plans of a workshop in New York State? We are talking to some folks in New York City. We're also talking to some folks in the New York State Master Teacher Program about setting something up for next year. Stay tuned. Unfortunately, there's a lot of uncertainty right now in education. And so folks are pushing the timeline out a little bit. Usually by now we'd have a little bit more to say, but it's going to come. We've been through this before. On that website that I gave you, bootstrapworld.org, there's a link that says workshops. As soon as something is on the calendar with the contract signed, we will post there. So definitely keep an eye out for it. We've got, I think, 90 seconds left. If there's any other questions. All right, that looks like it might be it. So folks, I deeply apologize for the technical difficulties that I've had here. I'm sorry for wasting the first 5 minutes, but I hope that this has been informative. I really want to make sure that nobody leaves here and says, Emmanuel is an asshole and he hates Scratch and he hates integration. Far from it. Integration is the way to go. It's the only way we're going to scale. It is the only way we're going to reach every child. We need to use the teachers that are already there, and we need to use the subjects that already reach every child. But there's no such thing as a free lunch. So if you want integration to succeed, we need to get off our bandwagon and join someone else's and find out what are the pain points for them and how can we make it better using subject-appropriate tools, curriculum, and pedagogy.